Hi everyone, my name is Xi Yang. I'm from North Carolina State University. Our paper is entitled Student Subtyping via EM Inverse Reinforcement Learning. During the student's learning process, they will make decisions following different strategies. For example, some students may seek to complete the learning task with minimal efforts, while other students may try to do as much work as possible by themselves. Such situations suggested that there exists intentional heterogeneity among the students. Discovering such heterogeneous intentions is important since it can shed some light for the tutor to adapt instructional interventions to improve students' learning. To model the heterogeneity, we did student subtyping to group the students based on their learning intentions. Specifically, we employed a method called Expectation Maximization Inverse Reinforcement Learning, or EMRL for short. Similar to the traditional reinforcement learning, it is able to estimate the long-term impact of each action. Meanwhile, like the general inverse reinforcement learning, it can infer the student's decision-making rewards. In addition, the introduction of the EM process enables it to model the intention of each group of students independently. Based on the EMRL, we got some interesting findings. First, in 3 simulation environments with the ground truth, EMRL could accurately group the trajectories by their intentions. This gave us the confidence to further apply it to an ITS environment. From students' longitudinal logs collected from an ITS, the EMRL learned the 3 student subtypes, which based on the statistical analysis were named as learning-oriented, efficient-oriented, and no learning. Besides, EMRL outperformed 3 other widely utilized subtyping approaches. Now let's look into more details of this problem. The student subtyping is widely analyzed in previous works. It is generally modeled as an unsupervised learning problem. For example, some previous works applied EM clustering and k-means to get the student subtypes. However, these methods were based on the static data without considering the dynamic properties during the learning process. In order to capture the dynamic information, there are in general 3 categories of methods, which are proximity-based, feature-based, and model-based methods. More specifically, in proximity-based methods, the similarity between the pairwise data is measured by a distance, which can be calculated by the methods like the dynamic time warping. In feature-based methods, the sequential data will be compressed into a feature vector, and then the static clustering methods like the k-means can be further applied. In model-based methods, the similarity of 2 data is measured based on the likelihood of one data given the model derived from the other data. Most of the dynamic methods do the clustering only based on the states, while in this paper, we subtype the students considering both states and actions during their decision-making process by EMRL. To introduce the EMRL, let's take a glimpse of the general reinforcement learning first. It is about how the agent learns the decision-making policies from interacting with the environment. During the learning, the agent first observes the state from the environment, then take an action, which will achieve a reward and update the state to state prime. The reward as a guidance will praise or punish the agent's behaviors, and the agent tries to learn a decision-making policy to maximize the expected cumulative rewards. As we can see, the rewards are crucial for the traditional RL. Similar like that, the labels are important for the supervised learning, especially most RL methods require the immediate reward for each state action pair. Generally, the rewards are handcrafted and carefully designed to reflect a certain task. For example, in video games like the Atari game, the rewards can be clearly defined as the scores. However, in more complex real-world applications, the rewards are quite complex and cumbersome to be manually designed. Specifically, in our application of the ITS scenario, the students' decisions are generally made based on a trade-off among various complex factors, for example, the time, learning gain, the difficulty of the problem, etc., which makes the reward function quite difficult to be manually designed beforehand. The inverse reinforcement learning can handle this problem when the reward function is unavailable. Just as in its name, it has an opposite direction comparing to the traditional RL. In traditional RL, given the rewards, we aim at learning a policy, while in inverse reinforcement learning, we are given a bunch of demonstrated trajectories. Then based on these demonstrations, the RL will automatically infer the reward function. Once the reward function is learned, we can then follow the traditional RL to further induce the policy. The inverse reinforcement learning has been widely applied in various applications. Especially, it has showed effectiveness in education domain. For example, it has been utilized to analyze the students' mastery of different skills from their decision-making records to find out their misunderstandings, so the tutor can render personalized feedback to improve the students' learning. In most of these applications, the intentions in the given trajectories are assumed to be unique and consistent. While in many cases, the demonstrated trajectories can be heterogeneous with multiple intentions. To handle the heterogeneity in trajectories, some previous works have been proposed, such as multitask-based RL, non-parametric Bayesian RL, and EM-based RL. Considering the efficiency and the performance of these three methods, we employed the EM-based RL in the following analysis. In the original EM-based RL, the number of clusters need to be predefined. In this work, we adapted it to a more general framework, which will automatically determine the number of clusters. In the following, I will give more technical details about the EMRL. The input of the EMRL consists of 4 tuples, including the state, action, transition probabilities between the states, and a discount factor for the future rewards. Unlike the traditional RL, the reward function in EMRL is unknown. Instead, it is given some demonstrated trajectories. Taking them as input, the EMRL will recursively cluster the students into different subtypes and learn the decision-making patterns for each subtype by RL until convergence. Here, we took the maximum likelihood RL at the M step. The MRL is a variation of the general RL. It aims at learning a reward function, which can be modeled as a linear function given the state and action, and it is parameterized by theta. Given the reward function, it will learn the Q value and the policy. Different from the standard Bellman equation, here the Q value is calculated based on the Boltzmann exploration. It enables the following objective function to be differentiable and makes the optimization easier. Then we further calculate the log likelihood, which measures the probability to observe the demonstrated trajectories. Here, the parameter rho stands for the weights of different trajectories, which can be estimated based on the frequency of the occurrence. Afterwards, the parameter theta will be updated. This procedure will be repeated until theta got converged. Then we further incorporated the MRL into the EMRL framework. Here, the parameter k stands for the cluster number, and the maximum number of cluster is denoted as kmax. Rho j and theta j stands for the prior probability and the reward parameter for the cluster j respectively. In each iteration, we first initialize the prior probability and the reward parameters. Then in the E step, we computed the probability that each trajectory belonging to different clusters. Then in the M step, the parameters rho and theta will be updated. Specifically, we employed the MLRL to update the theta. Actually, it can be replaced to any other RL methods. The EM iteration will be conducted until a stop criterion is satisfied. That is, the variation of the log likelihood for observing the demonstrated trajectory is smaller than a predefined threshold. Since the ground truths of the student subtypes are unknown in advance, it is difficult to directly evaluate the learned clusters from the student's data. As a result, we first carried out the EMRL in 3 simulation environments which have the decided ground truths. The 3 simulation environments are the grid world, highway, and a multi-car. And in each environment, the agent has multiple intentions. For example, in the grid world, the intentions can be either reaching the upper right, lower left, or lower right corners. Based on different intentions, we manually decide reward functions accordingly. In all 3 simulation environments, for each intention, we first learn the policy based on policy iteration, and then use the policy to collect a bunch of trajectories. Afterwards, the trajectories with different intentions were mixed together. The mixed trajectories were clustered by EMRL, and we measured the clustering results by the purity of each cluster and overall purity among all clusters. Specifically, the cluster-wise purity is calculated by the number of majority labels divided by the size of the cluster, and the overall purity is calculated by the mean purity of all clusters. Here show the results, especially in Great Wall and Highway. The trajectories with different intentions can be detected by EMRL completely correct. Given the effectiveness of EMRL showed in simulation environments, we are more confident to further apply it to the ITS environment. The tutor we explored is called Pyrenees. It is a web-based ITS teaching the students probability. There are 122 students involved in this study. Specifically, the students will follow 4 phases to learn, including reading the textbook, taking a pre-test, training with ITS, and afterwards taking a post-test. The learning performance is measured by the learning gain, which is calculated based on the pre- and post-test scores. To calculate the normalized learning gain, all the 20 problems in the post-test were considered. Besides, we also calculate the isomorphic normalized learning gain, which only consider the 40 of the 20 problems in the post-test, which are isomorphic with the pre-test. From the students' logs, we extracted 5 categories of features. Then we applied k-means to discretize the states for each of the category. Finally, we got 432 discrete states in total. The students can take 2 actions, asking the tutor to either elicit the solution or directly tell them the solution. After feeding the students' data into the EMRL model, we finally got 3 clusters. Based on the statistical analysis, we give the 3 clusters the subtyping names of learning-oriented, efficient-oriented, and no learning. A one-way ANOVA analysis on the pretest showed no significant difference among the 3 clusters, which indicated that the students in 3 clusters were balanced in their incoming competence. Regarding to the isomorphic normalized learning gain, there are significant difference among the 3 clusters, especially learning-oriented is higher than no learning, and the efficient-oriented is also higher than no learning. As for the NLG, we got similar results. The 3 clusters are significantly different. Learning-oriented has higher NLG than no learning, and the efficient-oriented is higher than no learning as well. For the time on task, the 3 clusters are also different with significance. The learning-oriented cluster takes longer time than the efficient-oriented, and it also takes longer time than the no-learning cluster. When checking the performance of the elicit steps, we found the learning-oriented cluster takes significantly more elicit steps than the no-learning. That is to say, the no-learning group of students tend to ask the tutor to directly tell them the solution. As a summary, the learning-oriented subtype takes significantly longer time than the other 2 groups and achieved good learning performance. It is suggested that they merely focus on learning the materials well, regardless of the time they spent. The no-learning group has significant lower learning performance and takes shorter time. It suggested that they did not take learning as the intention when training with ITS. The efficient-oriented cluster is a trade-off. They took significantly less time than the learning-oriented and still have a good learning performance. It suggested that they can balance the learning and time on task well. We further compared the EMRL to 3 traditional clustering methods, including 2 static k-means on either the pretest or final timestamp, and the dynamic methods based on the k-mods with the dynamic time warping distance. The 3 traditional methods were compared to the EMRL by log likelihood, which measured the probability to observe the clustering results. Our results showed that the 2 dynamic clustering methods are better than the static clustering methods. Among the 2 dynamic methods, the EMRL is better. It might be because that the dynamic time warping only considered the states, while EMRL takes both states and actions into consideration. According to these experimental results, we got the conclusions as follows. First, the EMRL could effectively learn the student subtypes reflecting their different learning intentions. Second, it showed the potential of providing tutors evidence to give more customized interventions to improve students' learning. Finally, as a future work, the EMRL learned clusters can be taken as labels and then be further combined with the supervised learning to accurately detect the students' subtypes in an early stage. Thank you.